So in this lecture, we'll be discussing on line integral of a vector and conservative vector field. Now, the integration of a tangential component of a vector along a line is called line integral of the vector along the given line. So this is the definition of line integral of a vector. Now, what does it mean? Now let us understand what is meant by this particular definition. Now, suppose f bar is a vector. So here is f bar is a vector quantity, and r bar is the given line. So again, you refer to this figure. So in this figure, r bar is the given line, which actually having two endpoints A and B. The direction of r bar at some point is given by the tangent dr bar at that point. So here dr bar actually represents the tangent direction of this particular curved line at any point. Therefore, component of f bar along the tangent dr bar is f bar dot dr bar, because dot product between f bar dot dr bar gives us the component of f bar along dr bar. Then by definition, that means following this definition, the line integral of f bar along r bar between the points A and B is given by integration between A and B f bar dot dr bar. Now, if we express this f bar and dr bar in terms of their Cartesian components, then you can write integration a to b I cap fx plus j cap fy plus k cap fz dot I cap dx plus j cap dy plus k cap dz, which stands for dr bar. So ultimately it becomes, taking the dot product, integration a to b fx dx plus fy dy plus fz dz. So this is the final expression of line integral of a vector along a line. Now, next there comes a problem. Now the problem says that if f bar is equal to grad of phi, where phi is equal to phi x, y, z is a scalar function, then show that number one, integration a to b f bar dot dr bar is independent of the path joining A and B. And number two, integration a to b f bar dot dr bar is equal to 0 around any closed path. So this is our problem. Actually, this problem will lead us to a very important definition which will be revealed gradually. Now let's first solve this problem. Now the solution of number one. Now here it is actually written as integration a to b f bar dot dr bar. Now you see f bar is actually given by grad of phi in the question. So if you replace f bar by grad of phi, then the integration becomes grad of phi integration a to b grad of phi dot dr bar. Now grad of phi dot dr bar is nothing but d phi, that means the total change in phi. So it is written as integration a to b d phi. Now integration of d phi is nothing but phi, so it becomes phi xyz integration limit from a to b. Now if you put the limits, so the result becomes phi of b minus phi of a. Now see, the result contains the value phi at the point B minus value of phi at the point A. So this is the result of this integration. Now, what does this result mean actually? This result means that it shows that the integral depends only on the endpoints A and B, as it is evident from this expression, and it does not depend on the path joining A and B. So here is the proof. The question was actually asked that you have to show that a to b integration f bar dot dr bar is independent of the path joining A and B, and so here is the proof. Now coming to question 2, or the second question, it says that integration a to b f bar dot dr bar is equal to 0, this is to be proved. So here you have to show that integration a to b f bar dot dr bar vanishes or it is equal to 0 along a closed path. Now the line integral along a closed path is actually given by this symbol, that means an encircled integral sign. So this closed line integral f bar dot dr bar actually represents the integration of f bar dot dr bar along a closed path. Now for a closed path, the points or the endpoints a and b coincide, because since it is a closed path, so its starting point and ending point will be coincident. Thus closed line integral f bar dot dr bar, as we know by this time, the result of this integration f bar dot dr bar is equal to phi of b minus phi of a. So you can write it as phi of b minus phi of a. But since the path is a closed path, so a is equal to b. So you can write it to be is equal to phi of a minus phi of a, and this is equal to 0. So here is the proof. So the integration of f bar dot dr bar along a closed path is equal to 0, where f bar is given by the gradient of a scalar quantity. Now, as I have said initially, this particular problem actually gives us the idea of the definition of a very important quantity, and that quantity is actually called conservative vector field. So if a vector is having all these three categories or all these three characteristics which are depicted in this equation, then that particular vector is called a conservative vector field. Again, I am repeating, if a vector contains all these three properties which are given in this equation or in this question, then that particular vector is called a conservative vector field. Now, what are the properties? Number one, the vector should be represented as the gradient of a scalar quantity. Second point is that the line integral of the vector between 2 points is independent of the path joining the 2 points A and B. And the third point is that the line integral of the vector along a closed path should be 0. So if the vector bears all these three characteristics, then the vector is called a conservative vector field. So you can see this particular problem is actually leading us to a very important definition of the conservative vector field. So here is the definition of conservative vector field. So it says, if the line integral of a vector f bar between 2 points A and B, that means integration a to b f bar dot dr bar, is independent of the path joining A and B, then f bar is called a conservative vector field. Also, line integral of a conservative vector field vanishes along a closed path. Now, in general, a conservative vector field is expressed as the gradient of a scalar function. Thus, if f bar is a conservative vector field, then it is given by f bar is equal to grad of phi, where phi is any scalar. So this is the definition of conservative vector field, and this definition we have actually got from this particular problem, or in other words, this problem actually helped us to understand the definition of conservative vector field. Thank you.